Right. So we're going to continue talking about bivariate distributions, and maybe some association of them through covariance. We're going to look at having linear combinations of different random variables, and the covariance becomes important in looking at sums or weighted averages and things, and do a little illustration of bivariate normal. So most of this is in 6.4 of the chapter. Collecting a homework today. I'll post one that we do sometime after break, but that's not quite ready yet. So on the handout, does everybody have a copy of the handout? So this, we last time looked a little bit at things related to well, let's do it like that. You can see the handout, right? That if you have two variables at once, they have a joint distribution. And if they're discrete, then the joint probability function gives the probability that x has a certain value and y has a certain value. And we went over last time to get the margins. Right. To get the margins of x, we add over the y values when they have that x and y combination. And to get the y values, we add over those. And then we can look at conditional distributions of one given the other. And if they're related to one another, they're not independent, if they have some correlation, then they, here you go, yeah. Then the conditional probabilities will change depending on the value of x. So the conditional distribution of y given x, as x changes, then the probability of the different y outcomes changes, and we see the association. And a lot of applied statistics dealing with surveys or categorical responses is really interested in how those probabilities are changing as different categories are changing. In general, if this relationship is true, then the probability of x and y together can be a probability of x times a conditional. If random variables are independent, then the probability of two things becomes the probability of the x variable's value times the probability of the y's, and it simplifies. If that's the case, then all of these conditional probabilities is just not going to change. As x changes, the probability of y is just the probability of y. It doesn't change. And the continuous versions are done with integrals. The density function for two variables together. To get the marginal for x, we integrate out y. To get the marginal for y, we integrate out x. And if we have the densities, the joint density and a marginal, we can get a conditional. And again, if they're independent, then the densities just multiply together, right? And there's a theorem we had, or a way to quickly check if variables are independent of one another. Well, for x and for the discrete ones, you really have to look at all values of x and all values of y to see if it works. If this xy was from some formula, we could essentially apply this factorization theorem as well. So if x and y are independent, then their density can be written as the density of x times the density of y. And it goes the other way too. If you can write the density, the joint density, as a function of x times a function of y, and separate them, right, multiplicatively, right, then in fact they are independent, right. And the one wrinkle in that sometimes, if there's a relationship between the range, if x has to be less than y or something like that, it makes it, you have to kind of look at it specially, right, because really there's some indicator there that you can't divide up. So, but otherwise, it does that, right? And so what we're looking at now really is this issue of expectation, right? If we have two random variables, we can take different functions of them, we can take the differences, we can take the ratios, the You multiply them together, and so on. And that's a new random variable. So it's a function of two random variables. It's going to be a new random variable. What's its average? What's its variance? After break, we're going to take up the question, what's its actual distribution? How do you actually find its probability distribution for different functions? Not just simple ones, not just the averages, but more complex ones. How do you actually determine what's the probability density once you take that function of things? Expectation, though, we can do of a particular function g of x, y. We can just evaluate that function at every combination of x and y and multiply the result of applying that function times the probabilities. And add those up, and it's a discrete probability expectation, just like before. Or with continuous ones, it's an integral. Right? It's the value g of x, y weighted by essentially the density, that f of x, y. You get that expectation, and you get the average value of that new variable. A special one is covariance. Right? The covariance of x and y, the function is x minus its mean times y minus its mean. And that particular function, so if we look at covariance of random variables x and y, covariance of x and y is defined as the expectation of x minus its mean times y minus its mean. Computational purposes, when we're doing integrals and stuff like that, we can, it's equivalent to just finding the expectation of x times y minus the product of the two means, right? Where the use of x is the expectation of just the x variable, and use of y is the expectation of just the y variable in there. But that interpretation of the covariance, right? If x and y tend to be larger than their averages together, and tend to be smaller than their averages together, so the sizes are going up and down generally together, and you get a positive covariance. But as one goes up, the other one tends to go down. If there's kind of that trade-off, linear trade-off, then you get a negative covariance. And so if we have a picture of the values of x versus the values of y, and here is the mean of x at that place, and the mean of y is kind of out here. If there's more probability up in, if there's more probability kind of up in this area, in that quadrant that's there, that x's, whatever these values are bigger than the mean, and also the y's are bigger than the mean. So the product of x minus that and x minus that, for the values up there, are both going to be positive. And if there's a lot of probability or density up there, right, then you're going to, that's going to be things that are added positively to the mean. Similarly, if a lot of the other values that have a lot of probability or density are down below, then you're going to accumulate a lot toward that expectation that's positive. Right? If there's little x minus its mean, so the x range minus its mean is in the negative zone here, but y relationship to its mean is in the positive zone, and so the product of x minus its mean versus y minus its mean is negative in those two areas. If there's not much density there, right, you get a positive covariance. But if there tends to be a trade-off, and that as x gets bigger, y gets bigger, and most of the density is in this way, then we'll get get a negative covariance, right, and it'll be not associated. So let's look at one example where we do some deal with one density, right, and figure out some of these expectations to go over the integration, and then we'll apply it to other cases that have more context, right? So as an example of doing this, let's say that f of x y is it as 8 over 81 times x times y, right, as a density, where 0 is less than x, less than y, is less than 3, and it equals 0 if that relationship does not hold as a density. So this space where we have this density, we can do kind of an xy plane here to show where this function is defined to be above 0. So, 0 to 3, right, that's a square here. Y goes from 0 to 3. Implicitly, x can go from 0 to 3, but x has to be less than y. So the place where they're equal would be here. And so this area here, y has to be bigger than x, so y has to be going up. So it's actually in this space. So this density, this probability density function actually exists on that. That's that little triangle there, right? Some things will exist between 0 and 1. Some joint things will be between a 0 and 1 box. But sometimes, you have one thing that's less than the other, like the first occurrence and then the second occurrence, and different things have these relationships. Just try an example, calculus with it without as much problem, but this way. So the question we're going to ask is, what is the covariance of random variables x and y? Are these random variables positively associated? I'll ask that question. How are these random variables associated? With one another. They tend to increase together, tend to decrease together. Before we do the calculations, any guesses? In the inside? Okay. The value of x, how is that going to influence the value of y, or the possibilities? Let's go through what we need to do. So to get the covariance, we're going to need the expectation of xy minus the expectation of x minus the expectation of y. To get the expectation of, we can do the first one, right? The expectation of xy. So it has to do an integral, double integral of x times y. That's our function, and we multiply it by the density. 8 over 81 times xy. And then we there's this one we have to pay attention to order a little bit. Right? We could do it dx, dy, or dy, dx either way, but because there's that restriction on this space, let's say we do x first. Now y on the outside goes from 0 to 3. I'm going to go back to that picture. Y goes from 0 to 3. But every time you have a value of y, right, where can x go? Right? X can't go from 0 to 3 as well because of that restriction. Right? If you have a value of y, x can just go from 0 up to y. The slope one thing. So x can go between 0 and 1 on the inside. So if we do want to do this integral, x, so once we have y, x can go from 0 up to y. And so that kind of does that little piece of the triangle. And then, given that we do that one, we can go, y can go from 0 to 3. So yeah, so we integrate this, so 0 to 3 on the outside, the 8 over 81. And we're integrating first with respect to x. Right, so y isn't going to be changing. But x is x squared, so we're going to get x cubed over 3, and we're going to evaluate that at x equals 0 to y. Y. We put y in there. I have 0 to 3, 8 over 81. Y goes into this, we get y to the 5th over 5, and so that's over 15 dy. So that's the integral that we're doing still to complete this. Does that work out? Is that? So we have an x squared, so it becomes x cubed over 3. We're putting y in. When x is 0, that goes away. When y is, when x equals y, it's y cubed, so y to the 5th. Y cubed, why did I put that? I don't think I need this 5 yet, right? Do I? Just 3. So just 3. When I put in y, it's just y 5th over 3. I was thinking about integrating. It's just y to the 5th. Okay. So if that's right, 8, this is 243 down here. Combine those. Then that would be a y to the 6th over 6. And that's evaluating from y going from 0 up to 3. So 243 is actually y 3 to the 5th. There's a lot of 3's that you're going to cancel. Right, so it actually, this is 8. There's 3 to the 6th here. This one is actually 3 to the 5th. And this is 6. And so there's actually all the 3's cancel. It just ends up being 4. If you work it out. So the expectation of x times y is actually 4. Right? You want to check that things are kind of plausible, right? Y goes from 0 to 3, x goes from 0 to 3, but is less than y. So at the maximum, or the minimum, it could be 0, 0 times 0, or 0 times anything. And then if they're both 3, it would be 9. So we should get an expectation of this product somewhere between 0 and 9. And it turns out to be like that. Right, so that's the first part. Right. We have to take the expectation of x. Now to get expectation of x, we might as well just get the marginal density of x. Right? So to do that, we're going to integrate just the density. No function, just the density. And get rid of y. Integrate y out of there. And we had this restriction, right? 0 less than x less than y less than 3. So at a value of y, well, sorry, at a value of x, right? Given x. All right, so here's this picture. Here's x, and here's y. So at a value of x, what's the density at x? We're given a value of x here. There's our x. We want to integrate out y, average over the possible values of y. It's like if we had a 2x2 table, it was like for a particular value of x, it'd be like adding over that row. But in this case, it's kind of integrating over that direction. For a given value of x, y can go from x up to 3, right? For a given value of x, right, y can go between x and 3. So because of this strange triangle geometry, right, we have to integrate in that particular case to make it work out. So 8 over 81x, then y squared over 2, and then x goes from, well, so y goes from the lower point is x and the upper point is 3. Right, so we're going to get rid of one of that 2 there. And so when y is 3, we're going to get 9x. And when y equals x, we're going to get x cubed. And I pulled the 2, canceled it into the 8, so that's not there. And so this works, right, for x over the full range. So that's the marginal for x. So then we can do the expectation of x the usual way. We can integrate over the range of x of x, right, that's the function, x by itself, times its own special density, 9x minus x cubed, which is just a polynomial. So if you do that, the expectation of x is equals 1.6. Right, again, plausibility check. X is between 0 and 3, so our expectation has to be between 0 and 3. 1.6 is down there. Right? The density also is going up because as x gets bigger, right, the density gets higher. So we're over 1.5. We're in the average is in the upper half because there's more density as x gets bigger. So, right. If you do a similar thing with y, I have the density of y written down. I'll just give you the answer, and you can, if you're interested in checking, the density for y ends up being 4y cubed over 81 for 0 and y less than 3. And the expected value of y, if you calculate that, ends up being 2.4. Right? So if we put everything together, the covariance of x and y, the expectation of x and y, minus expectation of x times expectation of y. We had 4, 1.6 for x, 2.4 for y. Ends up being 0.16, which is positive. So there seems to be a positive association between x and y. Turns out with this yeah.
In the previous, when we were calculating the expected value of x, is there a reason that we didn't just use a double integral? Why we?
No, you can use a double integral, right? So what you can actually do, right, is this 4 over 81, 9x minus x cubed. Instead of having that there, you could take this function and just stick it right there. And then it would be like a double integral. Right? So you can, right, this is equivalent to it, y going from 0 to 3. Oh, sorry, x going from 0 to 3. And then this thing going up to 3 of x, f of x, y, dy, dx. So you could write it that as a double integral. Right? Writing it this way, we kind of get the marginal density of x in case we wanted that for anything else along the way. But you're right. Effectively, it's a double integral doing one at a time. Right? So that's part of how these go. We want to see doing those after break when we do transformations. We'll have to do a little bit more of this to do one method of finding new distributions for by transforming things. So if the expectation of x, here's another logical check, right? So x has to be, y is bigger than x. So you would expect that the expectation of y is bigger than the expectation of x, right? So this one's 2.4 and it was 1.6 for x. If it had been reversed, it wouldn't make any sense, right? It would be an error, dropping a term. So this is positive. Can we think of any explanation why these things should be positively related? As x gets bigger, y gets bigger, or as y gets bigger, x gets bigger, or something like that. Part of it is this, yeah, go ahead.
Oh, just that like in the original function, they're both bigger than 0. And they're multiplied together, so it makes sense that if either one of them gets bigger, it's going to increase the value of the function overall.
Yeah, so if either one gets bigger, the value of the function gets bigger, right? And so if you have big values together, really make that function get bigger, and if they get smaller, the function really gets smaller. And so it's But, and that's, they think it's kind of a trade-off. So that's part of it. So that is, you know, if they're both big values, there's a lot of density up there when they're both big. There's also something to this, you know, it's something part of just this restriction here, right? So if X gets big, Y can't get very small. It has to be bigger, right? As X gets bigger, it pushes Y up. And similarly, it is if Y gets small, right, it pushes X down, right? It kind of squishes it. So as X gets bigger, Y, you know, they kind of go together in kind of a way, and that turns into a positive covariance. So anyway, right, so working through the calculus formulas, the intervals, following those, we get those examples. Yes?
Can the covariance really be like anything, or is there sort of like a range of values that are more typical to see?
So, covariance, what would be the units of measurement on covariance? Where would they get their units of measurement? There's a X and a Y, right? So covariance really can be anything. If you measure time in, you know, in days and switch, you know, as you switch to, you know, hours and minutes and seconds and milliseconds, the average number of milliseconds is going to be enormous for something that you're typically measuring days, but in the thousands or hundreds of thousands. And then covariance is going to be the hundreds of thousands as well. So covariance is sensitive to the units of measurement. But if it's greater than 0, it's positive, and there's kind of a positive association, whatever the scales are. If it's negative, there's a negative association. The other thing that gets done, right, that we will use is, and often use for thinking about things, is correlation. Okay. So often covariance is standardized by dividing by the standard deviations, right, so that if X or Y is measured on very different scales, you know, as you plot them on the computer, it adjusts, you know, whatever scale it is. It kind of fits it on the screen. And that's kind of the standard deviation adjustment. Correlation is between, turns out to be between -1 and 1. And when it's at 0, it's a covariance of 0, and they're uncorrelated with one another. They don't tend to go up or down together. It's positive covariance, it's positive correlation. And, you know, in applied statistics, you would look at a number of scatter plots of points. Some things are highly correlated with one another and get very strong correlations near one. Many things in physical sciences, where you're studying an input to a reaction and an output, and you're measuring the inputs and outputs, or outputs that are supposed to go together in a certain ratio. The correlation could be extremely high. In social sciences, economic sciences, things that are highly correlated are often related to size. You know, the number of people living in a community, the number of people, you know, that are over a certain age, the number of employees by an area, the value of income, the number of people, the number of businesses, all those things really go together, extremely highly correlated together. Other things are just, you know, can be strongly negatively correlated, but just, you know, are all different sorts of things. We're going to use covariance and correlation in two ways with linear combinations of random variables. Right. We'll use these two relationships, but let's talk about the general case. Right. So linear combinations of random variables, right, can be done in a very general way. And the book presents something in a very general way. So let's say you have some random variables, y1, y2, and yn, a bunch of measurements here. And you have a bunch of other measurements here, possibly. So you don't necessarily have to have the same number of variables in one, because you're measuring a bunch of variables at time period 1, and a bunch of variables at time period 2. Maybe these are different individuals, maybe they're different measurements of size or economic health or something that are made at 2 2 different time periods. We can take weighted combinations of these, so using the book's notation. Let's say we add these together, but we have some multipliers here. We're going to take some linear combination. It's called linear because we're going to put an A0. Let's make this even. An A0, some constant plus a multiplier times these. We could do a similar thing with the x's. So we have B0, B, I'm going to do L, K. I'm going to call it K. Right, for that index. So these couple of random variables, right? We could be interested in what's the average value of this combination. Maybe these are inputs, right? How much of a certain items are you using? And these are costs per item. Right? To build something, build a house, you need wood, you need nails, you need wire, you need people's time, you need bricks, everything like that. Maybe these are all measurements of the inputs. And these are the per unit price plus some kind of a fixed price. Right? What's the average of those things? Well, it turns out the expectation of this function is expectations of linear operator. We saw a few ways that expectation works. Before, for single variables, this is the way it works for linear combinations of other variables. The expectation of this linear combination is a linear combination just applied to the mean. That's great. That's might be how you would think about it would go. Right? The expectation of B has the same type of thing. Oops, I forgot a B. Okay, I forgot the multipliers. There. K equals 1, 2, M. If those are constants, right? In there, then expectation only applies to the random variables, right? And we did that. With linear, like this, it works out like that. The variance is a little more involved because variance, if you look through proofs about related to this are in the book over a couple of pages. For the relationship that happens for variance. Now the fixed cost, the A0, doesn't affect variance, right? You just shift all your values by adding, $100 to it. It doesn't change spread. It doesn't change the relative spread of the point. It's just a constant, right? So they're one way of representing it as a double integral, a double summation of the AI times AJ terms times the covariance of a YI, YJ. In the variance there's every variable, and there's a square. When you square that out, you get a YI, all the YI times YJ combinations match up at some point, and you expand it. And if you keep, YI minus its mean, YJ minus its mean, right, are in there, and then you get the covariance. But the extra term that's multiplying those, the AI continues through, and the AJ multiplier comes through, and so you get this weighted combination. Another way of writing this is, well, we can consider the cases where I equals J. You get an AI squared if it's the same one there. And I didn't mention it before, but the covariance of a variable with itself is actually variance, right? Because if you have a variable minus its mean times the other variable minus its mean, and they're the same variable, it's a variable minus mean squared, so it ends up being covariance. So this is the variance of a variable. And then another way of expressing it, so we have all those cases where I and J are different. And there's a symmetry here, that the covariance of YI with YJ is the same as the covariance of YJ with YI. It doesn't matter which order you write those in. So you could put 2 times the sum over the indexes I and j, so I less than j. You just only want half of them, and then a covariance. Ends up being the variance of this linear combination, right? So kind of a big formula. Right? In there, something similar happens to V, right? The variance, variance here, I'm writing, calling one of these things a V, I don't want to have confusion. So the variance of that V is going to be similar, except it's going to be a sum over the indices for that one, and there's going to be a V term here and covariance of the x's. Right? So I'll write that one just on the next page. So it turns out that the variance of that V combination, so I use k going from 1 to m, there'd be a V sub k squared, and then a variance of a particular x value, plus 2 times the cases where k is different. There's a V sub k, V sub l times covariance. So variance and covariance enters into this linear combination. And you can actually take the covariance between these 2 things. Right. The covariance between the sum of the y's and the sum of the x's, right? Where would you actually do something like this? Well, if x is a bunch of measurements at one time period, like the cost of building it in one time, and the x's are the cost of building at another time, right? They have averages, they have variances at each specific time, and there could be covariances, right? Things could be changing, so that the price of one thing is going up and another thing's going down, and so there could be maybe trade-offs. If you use more of one material, you can use less of another one, and so on, so there could be these trade-offs of these multivariate relationships. So you might be interested in the covariance of how these things go. So this formula, right, again, the constant charges don't matter. But this one, the U has all the x's, all the y's, and the V has all the x's, and when you multiply those together, you get all the cross products. Right? And so you end up with A sub I, B sub k, a covariance between each of these possible different So those are the big formulas, right, that do apply at some time. We're going to look at more specific formulas, right, special cases of this, where we can see what's going on. So on our handout are a couple of the formulas that we'll use more in practice. So instead of taking these big combinations, these big special formulas that are general also apply to a simple case where we just add 2 variables together or take the difference of 2 variables. So that's the complexity. We're going to mostly concentrate on these couple of simpler forms for this moment. So if you take 2 variables x and y and add them together, well, the average of that sum is just the sum of the 2 averages. The difference of the averages is just the difference of the averages. So what the formulas say, the variance of this sum is not just simply the sum of the variances. Right? There's this extra covariance term between the 2 variables that and or the difference, because of that negative, you end up minusing. Like the -1 is 1 and -1 are like the A1 and A2 multipliers there. And so you get a negative covariance there. Depending on how the covariance goes, is it positive or negative, is going to be crucial in terms of what happened to that ultimate variance. So let's look at one further example. So our special cases that we'll look at. So x plus y y, then the expectation of x plus y, the expectation of x plus the expectation of y, and the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x. The other thing we might do is take an average. We average two things together, what happens? Well, the expectation of x plus y over 2, that 1/2 in there, this is like having 1/2 times x plus 1/2 times y. So it's like having x, two variables with the multipliers a1 and a2 are both 1/2, right? So this ends up just being 1/2, the expectation of x plus the expectation of y. What's the variance of the average? Well, that 1/2 out there, in variances, when you multiply by something, it gets squared. Variance is always squared. So you end up with a 1/4. Variance of x plus variance of y plus 2 times the covariance of x. That's going to be that. So imagine that we're measuring somebody's blood pressure. Blood pressure is kind of actually a fairly highly variable measurement. So if you're doing a scientific study about health and biological health, you might want to take multiple measurements. So let's say we take two measurements of blood pressure. And systolic or diastolic. Thinking about diastolic blood pressure in this example. Say the first time the average is 80 and the standard deviation is 6. And the second time, typically in a population of generally healthy adults that are kind of near the guidelines, 82, again a standard deviation of 6. And there's a correlation between the measurements. 0.8. What does it look like, the distribution of the average? We average the first and second values. Together, what's the expected value of our measurement? What's the variance of it? Do we gain anything by measuring twice and taking an average? How much do we gain? What's the expected value? So if this is x is the first measurement, y is the second measurement, we average these two things together. The expected value of the average is just the average of the two measurements, right, of the two average values. So it's going to be about 81 on average. Diastolic blood pressure. Average. What's the variance of our average? What's the 1/4? And the variance of x. So if the standard deviation is 6, the variance is 36. Same thing over here. The variance is 36 for the second one. So there's 36 for the variance of x, 36 for the variance of y. But right, that's not the end of the story. There's more to it. We have to have the covariance in there, right? If the correlation is 0.8, then the covariance is the correlation times the standard deviation of x times the standard deviation of y. So the correlation is the covariance divided by the standard deviation, so you can figure out the covariance if you know the correlation of the two standard deviations. So there's going to be the correlation is if it's 0.8, right? That would say that the people with high blood pressure tend to have high blood pressure on both measurements. People with low blood pressure tend to have low blood pressure on both measurements. Standard deviation of 6, standard deviation of 6. Right, and you get that.
Shouldn't the covariance part be multiplied by 2?
2, yes.
Are we using correlation or covariance in the second part?
This is the correlation figures in there, but it's covariance that gets added in. So in these previous things, this was always supposed to be your B. Covariance.
Okay.
So throughout, variances are on the same square root as covariances. I don't see anything. These is a covariant. These are B's. Yep, so the covariances become the terms. The correlation is the one that's standardized. So in this numerical example, you get the 2 there. This thing, the variance of this average ends up being 32.4. And so the variance of the average, or the square root of that thing, and I'm kind of run out of space. So we're going to take the average of the 2 blood pressure measurements. The expected value of this thing, x plus y over 2 is 81. The variance of this average using those formulas is the 32.4. The standard deviation of those things is the square root of that. The square root of 32.4 is about 5.7. And so this so this average is less variable than each individual measurement, but not a whole lot less. Why is it not a whole lot less? The reason that it wasn't a whole lot less is because not only you have the first variance and the second variance, we have this other big covariance term added in there. A higher correlation to adding them together meant that the total variance, right, had this extra boost in here that made it so that the sum is even more variable. It's compensated by taking the average, but it's still not as accurate as just 2 things that were independent of one another. Right, so it does affect things there. Right? But any questions? So that's how the formula works for one of these examples. Another example that's kind of interesting to look at. So, kind of a conclusion of these. Generally, it's good to take averages. It tends to make things decrease in variance by taking averages of things, right? That's generally more precise, right? But if the measurements are highly correlated with one another, the big ones tend to be associated with other big ones, and the small ones with other small ones, and variance doesn't decrease nearly as fast as you might hope. But this covariance can be a very substantial part of impacting measurements. The other, one other kind of example that's kind of interesting, right? We can think about stocks a little bit. Right, so if you had 2 stocks that you're going to invest in, and one is, the returns on a stock are roughly normally distributed. The mean is a gain of about 3%, and the standard deviation of those measures is about 0.02. This means that the variance, if you square that, is 0.02 squared or 0.0004. Small number. You have a second stock that has a mean of about 5% and a standard deviation of 0.03. That means the variance of that stock, that thing squared, is 0.00009. But the correlation between these two things, these two measurements, is negative. Right, negative 0.4. Why would you get a negative correlation between two stocks? Well, if they're kind of in opposing industries, right? If one tends to go up when the other one goes down, maybe they're competitors, like they're MasterCard and Visa. As one does well, it dominates the other one tends to go down. Maybe one is, benefits from high gas prices. Their production of gas and oil. And so as prices go up, it benefits, but that hurts trucking. Right? That relies on lower, right? So these industries or something are trading off. And now you have a choice to make. How are you going to invest your money? Are you going to pick this stock? Are you going to pick this stock? Or are you going to do something different? Right, this one has a higher return, right? But it has more variability, right? So it could have a bigger chance of being negative or being less, right? It's like, is there something that would do a little bit, better? Well, what if we just average them together? We're going to consider maybe a new option, y1 plus y2 over 2. There's half the money in one, half the money in the other. How do we end up? What's the result? Right? What's our expected return? For averages, it's just the average of these two returns. So you'd be at 4%. 0.03 plus 0.05 over 2, so about 4%. So that's better than one stock, but it's less than the other one. So variance is going to be important. What's the variance? What's the variance, the average for us here? Well, there's a 1/4 out here, a variance of y1 plus a variance of y2. Now, it's it's negative, right? So, well, plus 2 times the covariance, y1, y2. COV. But that covariance is negative because the correlation is negative, right? So you're putting these two things together that are negatively related, and so as one goes up, the other one goes down. So it dampens the variability. Right? The covariance of y1, y2 is the correlation, negative 0.4, right, times the 2 standard deviations. Right? So there's a 0.02, 0.003 here. Is the covariance. So we want this whole formula here. I'm going to move this one all the way back over here. So 1/4, the variance, the first one is 0.0004. The second one was 0.0009. Then covariance is negative. There's 2 times 0.4 times 0.02 times 0.03. Quite right before in my notes. So let's see what it comes out to be there. So we want 1/4 times 0.0004 plus 0.2009 minus 2 times the covariance, so 0.4 times 0.02 times 0.03. So that's the variance. And the square root of that, oops, will be the standard deviation of this new thing, so 0.014. So 0.000205. So it looks like the variance is 0.000205. And then so the standard deviation, the square root of that, 0.0143. 0.0143. So taking this average, we get a lower return, right? 4%. than the most conservative one, right? Than the 3%. But our variance, our standard deviation, is less than either one of these. So you're very likely to be, you're more likely to be close to that return. If you try to draw densities related to this, negative 0.01, 0, 0, do a number line here, and then that's about 0.11, 0.10. The one that's centered at 0.05, that second stock is quite variable. And it was centered here. Y2, the average for Y2 was here. But it could stretch, all the way up here. Standard deviation of 0.03, right, 2 times that puts you up at 11%, minus 2 times that puts you down at negative 0.01, right? And so there's a little bit of probability that you're going to be negative out here and lose money. The other one that was centered at 0.03, right, that gives us the value of 1, the first one I said. I had a standard deviation of 0.2, right? So it can go here, maybe up to about here. Yeah, it's going to be a little bit higher because it's a little more narrow, right, the normal. And then, but it also kind of comes down here to about 0.01, right? Going down 2 standard deviations is down there. Right? What about our other one? What about our average? Right? And our average one is one that we call X. It's here at 0.04. That's the average for the X variable. Is it going to give you a return, or is it very likely to give you a return that's negative? The standard deviation about 0.14, so it's not going to have much probability below 1. 1.4, about 1.5, about that. So, and then up to 0.07, I guess, is here. So it's gonna be even a little higher because it's a little more narrow, right? So, but its distribution is going to be kind of like this. So most of its probability, right, is clearly positive. It doesn't have quite the potential of that one, that had 0.05 as an average. If you really like to gamble and you really like risk and maybe the big return, maybe you'd want to put it all into this one and just hope that you're up here. Right? But even if you're really conservative and say, I don't want to have that much variability and risk, you still probably want to do this one. Because this one that's the average is beating this one, both in terms of average and variability, and looks like a better choice. And why is it turning out to do that? Right? Covariance, right? The correlation is really driving it in that formula. You might ask, right? Yeah, so anyway, that's any questions about the basic formulas, right? So we used our special case, right? So and this average that forms for the linear combination, the average of the two is just the average of those. To get the variance, we had to have this formula with the covariance in there, and then the negative one ended up making it smaller. Is it best, can we do better than an average? We could push this, right? So we said x is y1 plus y2 over 2. All right, we could take some alternative. Say we had some probability p between 0 and 1. You could take p times y1 plus 1 minus p times y2 and say, maybe we like that better. You know, is there a very bad value of p that's going to be preferred? Well, for whatever this is, the expected value, let's call this one, I guess, w, for kind of a weighted average, was p times 0.03 plus 1 minus p times 0.05 as the new average. The new variance of this thing is, well, instead of having the 1/2 and getting the 1/4, you get a p squared times the variance of the first one. There's a 1 minus p squared times the variance of the second one. Plus there's 2 times the covariance, a p, 1 minus p, 2 multipliers get out there, times the covariance of these two things. Now, so we have expectation and variance. Right? Those are two separate measures, right? If we want to get the biggest average, we're going to choose p equals 0 and put it all in 0.05. Right? If we want the smallest variance, well, maybe we can minimize, choose value p to minimize this. But it's possible in probability and statistics to think about both at once. Right? So the biggest is we have is 0.05. You can think about really having two goals.
Did you go back?
Yes. We can think about having a couple of goals. Right? If you want a high average with low variability, right? Or low variability means minimize this one. Solve for p to minimize this thing. And it's not going to be all in one stock or the other. It's going to be some averaging to make it work out. We also want a high average. So we need to create some type of function, some way to look at this that both incorporates average and variance. So really there's two goals. We want to be near 0.5 if we can. So if we look at, the maximum we can do minus what we get by doing a weighted average. What's the weighted average? P times 0.3 plus 1 minus p times 0.5. We're going to square that, right? It could be, we're always going to be less than 0.05. If we square it, it kind of measures how far we are from it. This is just something I'm kind of making up. There's a kind of in estimation, we talk about bias, and we often do something called squared bias. But this is, this is our goal. We want to be up near there. We don't want to be too far away. If we move smaller, that's going to get bigger and bigger and bigger, and we don't like it. Right? So we want to make this small. The smallest, of course, is putting everything at 0.05, making p equals 0, but we know that doesn't work so well for variance. So we also want small variance as the other goal. So let's combine those and say we're going to take the variance from the other page plus this thing. It's not really I'm just going to put a box here and draw an arrow to that thing. So I'm going to write it. So we take the variance plus that thing. We get this big long expression with p, 1 minus p, and these squares, and so on. We could find the value of p to make that the smallest. Right? So we're kind of simultaneously trying to produce a small variance and a large average. Right? We want to minimize this thing over p. It's a quadratic because there's only p and p squares in there, so you could do it analytically. right? But we can use R. You can't use numerical methods to get, P is only one variable. So we can do things in R to try to look at that, right? And so that's what this bit here is. You don't have a handout of this, but it's loaded up. Let's see. So the variance is not completely correct, right, in here in my little function. So I want to evaluate my little argument here at different values of P and choose the one that gives me the smallest. So one thing I can do in R is write a little function. It could be a function of my whatever P is. I'm just going to call my function P FNC for function, right? A little abbreviation there. And the difference from 0.05 squared is there, right? 0.05 minus the weighted average squared. Right? And the variance, right, is something like this, but I forgot the covariance in here when I put it in. There's 0.4 should be there, right? So that's 0.02 was the standard. That's the variance. This is the variance. The p squared 4 minus p squared minus 2 times the covariance. Yeah.
Does it need to be negative 0.4?
I put the negative up here.
Okay.
Right. To have the negative out there. But yeah, it's negative. That negative is there exactly because of the covariance. It's negative, right? So that's my function. So when I run that part, I get a new object up here in my environment called the function, P function. Right? So if any value I put in there, like 0.5, right, it will give me a value of that function. This is not a variance because I have that extra bias T or the difference between 0.5 in there, but that's the value when it's 0.5. Right? If I set up a sequence of values, this thing sets up a big sequence of values. I can evaluate, this thing will evaluate that function at every value of those p's. Right? So this sequence, my p now is, right, all these decimals. And so if I plot the p versus the function at that value and connect it with a nice little line, that's an L there, right, it gives me a plot. And there's the plot of my function that trades off the difference from 0.5, kind of difference from the average I would get taking the best guy, versus the variance, right? And it looks like the minimum is pretty close to 0.5, but it might not exactly. But it looks like somewhere between 0.45, 0.55, kind of eyeballing it. So if I can make it redo this, but now make my sequences, my steps of things a little more precise, right? I'm searching for that p that makes the minimum. So I think it's in here, and I'm going to put a little more dense part there and make my plot. Right? Oh, so I'm still in there. So there's still that minimum there. And we know that this thing's quadratic and p squared, 1 minus p squared, so it's going to have this nice quadratic form. So I know it's not going to have, wiggles and things like that. So it looks like it's in there. And I did these numbers based on the old one. So that's 0.5, 0.52. It looks like it's bigger than 0.52. So I need to adjust this a little bit. So 5.2 to 5.25 maybe. All right. So let's see. Now I'm doing little steps that are pretty small here. I know the minimum is still in there. And then you can even do it a little bit more. 5.23, near 5.23. So 5. 5, 2, 2, 5, up to 5, 2, 3, 5, something like that. Right? Really, really small steps. Right? So the minimum is right in here. The C bind is actually going to, bind together P4 and the evaluation of the function at P4. And then I'm just going to select the row where equals the smallest value. Right? And so what that gets me is not the numbers I had from before when I forgot covariance, but it gets these values. Right? So that the minimum p value, the p min, the minimum occurs at that point. And if these numbers will be wrong because of that. Right? So that's the value, 0.522938, to my numerical precision where the minimum occurs, right? It's not, and the average return that I would get there is 0.3954. So it's a little bit less than 50-50, right, on the big stock. It's a little bit more than 50% on the lower stock that had smaller variance. It's kind of favoring the smaller variance. So it doesn't exactly split between 0.3 and 0.5, but it's a little bit less. My return is almost 4. If this is the correct variance, I think I need the 0.4 in there. Right? And I calculate the standard deviation. My standard deviation is now 0.139. So I almost get 4 as an average. I get a little bit smaller standard deviation than when I was at 50-50. Right? And so I kind of do both things at once. But it incorporates the variance and the covariances in there. And so, you know, you imagine these investment houses not looking at 2 stocks, but looking at 50 or 100 stocks and trying to maximize something like this. And they're looking at covariances, correlations, and other concerns. But a big part of it is simple. Covariance and correlations and how you weight things together. Right? So you can do a lot better than just taking individuals by taking some average. But any questions about that? So a special pair of variables, such as the bivariate relationship, the last thing for today is called bivariate normal. So if X is normal, say if I write that X a little tilde up, your normal with use of X and standard deviation for variance. Right, its density function, as we've seen, has a 2 pi sigma squared out here, square root of all that. And there's an e to negative 1 over 2 sigma squared. And then x minus its mean squared. And this is a bell-shaped curve, right, centered at use of x, where the length of the spread is about 2 standard deviations above and 2 standard deviations below. It goes off to positive, negative, to positive infinity, but there's very little probability after, 3, 4 standard deviations above or 3 or 4 below. About 95% of it is about plus or minus about 2. And so the average is that, the variance is the sigma squared, and we use the normal probability to get the y variable. Let's say that's normal. Then its density has a comparable form. A little x there and a little y there. Could be another bell-shaped curve. It might be higher or lower or things like that, but it has its variance in there. And the values of y can go between negative infinity and positive infinity. But if you take both variables at once, they can be jointly normally distributed, and that's a special density function. So if x and y are bivariate normal, they have a mean for x and a mean for y. Some people write like a normal with 2 dimensions to it. Sometimes with the dimensions down here to keep track of them. There's a variance for x and a variance for y. There's also a covariance between these 2. So the way you usually see it is something like this. Once you get into bivariate, multivariate things, people start to use matrices, vectors, and stuff like that. We won't do too much with that, but that's how you usually see it represented. Where this sigma xy is the covariance between x and y. And there's a correlation, right, between these two things. The correlation is covariance divided by the two standard deviations. And the joint density f of xy function is on the handout. So on the second full page of the handout, right there it is. Right? If you multiply two densities together, right, both of them had a square root of 2 pi, so 2 pi ends up there. Both of them had a standard deviation, sigma 1, well, sigma 1 squared, the square root of that, so both of them are there. Plus there's this correlation thing, enters the density, that's going to affect things. And there's e to the negative something over 2, kind of like what there's a quadratic form from before. We had just one variable, right? Right, x minus my mu squared, this is called the quadratic form. X minus mu squared, quadratic. And same thing, there's a quadratic form in there, and that gives it that L-shaped curve. In the joint density, you have a quadratic for the first one, and a quadratic for the second one. Plus there's this second term here that looks like a covariance, y minus, the first one minus the mean of the second one. That's the density. Right? That's the joint density of things that are normal. Right? These are some pictures of what that density function looks like. Right? This is a book that we used last fall, or previous fall, in the fall, for mathematical statistics, which is 252, would be a very appropriate course. After this one, this is actually in the second edition of that book, and now they're on to a new edition. But in the second edition, they have these nice pictures of that normal density function. Right, so both of these are centered at means of 0 in both variables, and standard deviations of 1. So both of them kind of go, if you kind of projected it onto one dimension, one axis, between 0 and 2, plus or minus 2, right, in each one. And if they have correlation 0, then it's kind of accumulating kind of an equal rate all along, right? It doesn't matter which direction you're looking. But as you get correlation, then it starts to pile up in the direction where x and y are along the xy axis, where they're equal. Right? And so this one is 0.3, so there's not much. 0.6, it starts to get a little higher. And then 0.9, the probability is really smashed up against that y equals x line. That's what that curve is, kind of in 3 dimensions. And one way to think about that is if you draw level curves to look at a 3-dimensional thing, what you do is you take a certain height of that curve and chop this, kind of mound, this mountain thing, and chop it off and say, what does the trace look like around the top? And that's called a level curve for this density. For this one, since it's kind of equal spread and not tilted in any way, you chop it, you get circles. And as you chop at the top, you get a little circle where there's high density, you chop down a little bit lower, you get, right? And so it produced level curves that look like this. But once there's correlation, those peaks up there are, this is where x and y, this is where x is big and y is big. It's tilted along those coordinates. Right? So as you're, particularly this, so as you're chopping this one, right, those things are very narrow ellipses because x and y are associated with one another. And it's unlikely to get an extreme x, extremely high x and extremely low y. It just not happen so much. So that level curves start to tilt. And what this means for applied statistics, if you're getting data from x and y that were associated and roughly normally distributed, you'd get samples of points in the xy plane that would kind of follow that. Right? So if you get 100 independent pairs, right, that are mean 0, variance 1, so kind of between -2 and 2. Here's one extra larger point, just happens by chance. right? And it's just kind of a random spread there without much pattern. Right? But as you get correlation and more correlation and more correlation, the points that you actually measurement on individuals tend to be values that follow that same pattern in the probability. So the density can be related to what things look like in reality. Our measurements of blood pressure, if they're highly correlated with one another, you get one high measurement, you get another high measurement, and pairs kind of look like that. You get couples, of any sort, and look at body mass index of one individual versus another. If they're kind of associated and kind of similar within couples, you'd have more correlation like this. But if they're really independent, very different from one another, if roommates are randomly put together by the registrar, there's not really any reason that they should be associated in any way in terms of these measurements, height or weight or length of hair or anything like that. Then they wouldn't necessarily be associated. So the normals are.
Can you actually go to the bottom of that last slide?
Yeah, this one?
No.
Oh, the previous
next
one.
slide too.
Go back here. So this bivariate normal. It has means, it has variances, and somehow it gets expressed that there's a covariance or correlation between these two variables. All right, thanks. Now the special thing about bivariate normals, right, is that linear combinations of normals are still normal, no matter what linear combination you do. So you can take the different, if the measurements start out with bell-shaped curves, different means, different variances, correlated or not. You take the averages or differences or any other weighted linear combination, you still get normals. It doesn't happen with other variables. Right? You do other things with gamma or beta or these other things that we've looked at. You linear combinations of those, and they deviate from the basic form that they came from. Right? And you can't use probability then. But normals are special because any linear combinations of normals still stay normal. And in fact, it's the only type of distribution that works for. So in books on multivariate statistics, right, there's whole books on multivariate statistics of looking at relationships of multiple variables and judging how they're associated and graphed and computing probabilities and things. It's kind of given as a characterization of a multivariate normal. If you have a group of variables that individually are normal, so that any projection of them, any combination of them, any linear combination is still normal, then it had to be normal to begin with. So if we have two variables, x and y, they're both normal, correlated or not, right? And we take some linear combination, a times x plus b times y plus some constant. L is a random variable, and L is still normal. So you figure out the expectation of L is a times average of x plus b times y plus c. The variance of L is L. Well, there's a variance of x. A squared. A squared times the variance of x. X squared plus b squared times the sigma y squared. Now the shift, the constant doesn't change variability. It moves everything, right? Up by a constant amount, right? It doesn't change relative spread of anything. But it is a 2 times a b times the covariance. Right? In there. So we figure out this. And this, and then L is still normally distributed. So, if you want to calculate probabilities, you can z-score things and use the normal tables. And it works out quite well. So that's a big example of one, and this normal linear relationships is the basis of things like linear regression and some of those methods of estimating relationships and prediction. So but at the heart of it is this bivariate, multivariate, normal model, right? But that's just, that's what we want to do for today, right? So that's really done a lot with this linear combination. We'll come back after break and look at conditioning and hierarchical models for nominal situations. I think the homework for today is really drop that off before you go on break.
Oh, yeah. What time?
Well, I have time
All right. Oh, you do not have managerial today?
No, we are
Yeah, almost forgot.
For some reason, I thought you said calculus exam, which obviously I should know you're taking all the calculus.
Taking all the calculus, take here.
Well, it's math,
I occasionally run into people in my Calc 1 class, and I was like the only one in Calc 1 class who really
and Sarah
liked
last
Calc,
time.
you know?
I was next to
And so like,
Melanie.
they were sort of aware that I was gonna
Except freshman year,
Calc
there's a
too, so like I
course
ran
where
into them
it
this
does
semester, and they'd be
Hey.
like, oh, are you taking Calc 2? And I'm like, yeah. And then the semester after that, they're like, oh, are you taking Calc 3?
This is a great.
And I was like, yeah. And then I ran into some of them this semester, and they're like, oh, you're taking more Calc? And I was like, guys, there's no more Calc. Like, what do you think? Math isn't just calculus,
Yeah,
like
thank you.
calculus 1 through 10. Like, Super, you
It's
too.
fine though,
Thank
we
you.
have, differential equations.
Have a good break.
You too.
All right.